ionic nature of covalent bonds, which is also called as dipole moment. Now, we've studied about covalent bonds, and second half of the chapter mein we'll study about ionic bonds. Before we directly jump into the topic, remember people, no bond, we've said this, but no bond is 100% ionic or 100% covalent. आज हम क्या सीखेंगे, how though a bond is covalent, there will be some or the other ionic part or ionic charge in a covalent bond. Now, let's study this with an example. Let's say I have HCl. So I know that NH and Cl के बीच में there is a covalent bond. Okay. Now, if I look at the electronegativity, we know that chlorine is more electronegative compared to hydrogen. Chlorine is more electronegative. And what is the tendency, or what is electronegativity? Electronegativity is the tendency to pull the electron pair towards itself. Now what happens here is, ये जो sharing of electrons है, it is not equal, that sharing is unequal. Electrons are closer, you can say वो जो shared electron cloud होता है, that is closer to chlorine as compared to hydrogen. We did some of this in periodic table. So जो shared electron pair है, it is closer to chlorine compared to hydrogen. Now since it is closer to chlorine, chlorine here develops a partial negative charge, and an equal magnitude but positive charge is developed on hydrogen. This development of charge is called as, polarity. And such a bond where this charge is developed is called as a polar bond, or you can say it is called as a polar covalent bond. And this is an extremely important phenomena. It is one of the concepts which explains why water doesn't mix with oil or oil doesn't mix with water, because of the difference in the nature of their polarity. Now, in order to express this, or bond polarity express करने के लिए, what we do is, in HCl we show an arrow from the more electronegative element to the, from the less electronegative element to the more electronegative element, and this phenomena is called as a dipole. Now, as the name suggests, dipole, di means two, pole means polarity. A dipole is product of the magnitude of the charge developed. I repeat, यहाँ पे जैसे डेल्टा पॉजिटिव था, यहाँ पे चार्ज था डेल्टा नेगेटिव. So it is the product of magnitude of the charge, because दोनों का magnitude same है, only thing different is the sign. For example, this is delta positive, this is delta negative. So dipole is the magnitude of charge developed times the distance between the charge. I repeat, dipole is the magnitude of charge developed and the distance between the charge. So let's say ये हमारे पास, I have two charge, यहाँ पे some delta positive, यहाँ पे कोई delta negative, and the distance between the two is d. Then the dipole moment, which is also given by the symbol mu, will be given as the magnitude of the charge into distance d. With me till here? Now, the unit for measuring dipole, there are two units. the first unit, dipole is given by the symbol mu. So dipole moment at the first unit is ESU centimeter. ESU stands for electrostatic unit. Electrostatic unit centimeter, and this is the full form for ESU, and it is also given by Coulomb meter. इसको हम ऐसे भी लिख सकते हैं, Coulomb meter. Now there's one more unit given for the name of the scientist who gave dipole moment, which is called as dB. 1 dB or 1 d, dipole moment is also given in terms of dB, is equal to 10 raised to minus 18 ESU centimeter, or 3.335 into 10 raised to minus 30 Coulomb meter. We need this unit because eventually we have to do sort of sums based on dipole. With me till here? Now, dipole is a vector quantity, and I'm sure physics में आपने vector product of two vectors किया है. So let's say I have एक vector ऐसे, okay, and let's say this is some vector which is in this direction. Let's say I call this as vector A, and this is vector B, and the angle between vector A and B is theta. So what is vector product of the two vectors? वो net resultant vector का यहाँ पे what will the formula be? So the net resultant is given by the formula under root of a square plus b square plus 2ab cos theta. आप लोगों ने पढ़ा है ये in physics, vector product of two vectors. Why? Because when you talk about bond polarity, we will discuss what will be when we talk about polyatomic molecules. तो हमें एक resultant vector ढूंढना होगा. For example, जब हमने HCl में देखा, in HCl there's only one vector in one particular direction. But let's say I want to compare this with, I want to find the net dipole for a polyatomic molecule. For a polyatomic molecule, let's say, is CO2. Now, why are we actually studying dipole? See, hybridization and valential electron pair theory say we can theoretically determine what would be the shape or geometry of a molecule. For example, we have learned CO2 is a linear molecule and its hybridization is sp. And theoretically, I can also say that the bond angle is 180 degrees. Now, how do I experimentally verify this? Dipoles helps us experimentally verify B. See, CO2, so in carbon and oxygen, who's more electronegative? Oxygen is more electronegative, so the dipole direction will be like this, going from the electropositive element to the electronegative element. Similarly, यहाँ पे the dipole will be in this direction, going from the electropositive element to the electronegative element. Both the dipoles have the same magnitude. तो इसका भी अगर मैं बोलूँ, let's say magnitude A है, इसका भी magnitude. Now I want to know what is the resultant dipole. Though physics में क्या रहेगा? See, both are in opposite direction, same magnitude. They are going to cancel each other. But if I can substitute that in that formula to find the net dipole निकालने के लिए, what will the formula be? A square plus b square plus 2 AB. Now B is also A over here into cos theta. How much is the angle? So net dipole यहाँ पे, what is A square plus A square? This will become 2A square plus again 2A square. And what is cos pi or cos 180? So net dipole क्या बन जा रहा है यहाँ पे? 0. You can experimentally check this, whether CO2 has some or the other form of magnetic character B, dipole character. All this can be experimentally checked, theoretically verified. That also tells us that the theory that we have learned in terms of hybridization and valence shell electron pair repulsion theory, वो theory correct है. So one of the most important applications of dipole moment is it helps us identify the structure and geometry of molecule. Okay, this is CO2. Now we have to try for different molecules. Now let's try the next molecule. Boron trifluoride, BF3. In BF3, what was the hybridization of BF3? BF3 hybridization was sp2 and the geometry was trigonal planar. So this looks something like this. I have B, 1F over here, 1 over here and 1 over here. This is BF3. Now fluorine and boron, who's more electronegative? It's obviously fluorine, most electronegative element in the periodic table. So ये first dipole is in this direction. ये boron और ये fluorine का dipole will also be in this direction. This boron and this fluorine का dipole is also in this direction. So we can see over here that there are 3 dipoles. But मुझे तो निकालना है BF3 का net resultant. So what I will do is, look at this. Remember, all 3 of them have the same magnitude. So इसका magnitude A है, इसका magnitude A and A. Okay. Now, this A and this A, what is the angle between the two? What is the angle between the two? Excellent. It is 120. So ये A और ये A का, we need to find the resultant dipole. I repeat, ये A and ये A का resultant dipole. How will that look like? Sorry, उसका पहले निकालते हैं value. So that will be A square plus A square plus 2 A cos 120. Can I directly write cos 120 as cos of 90 plus theta? And I think maths में आपने किया है, ये basics में all silver teacups. Cos 90 plus theta is how much? Minus sin 30. And how much will sin 30 be? So वो हो जाएगा A square plus A square. This becomes 2A square plus 2A squared into minus half, because यहाँ पे this becomes minus sin 30. So ये 2 कट हुआ, 2A square minus A square, तो क्या मिला again people? Root of A square. That is, in short, इन दोनों का जो net dipole है people, it will also be in this direction. I don't know if you got that. I repeat, ये A और ये A का, this is the net resultant. Now what happens here is, and this net resultant का magnitude is also A. Now this net resultant A and this net resultant A, both will cancel each other, and BF3 का net dipole is also 0. Did you get that? Yes or no? You can get questions like, or exam में ऐसे आते हैं, which among the following molecules have net dipole 0, net dipole not 0? planar molecule, non-planar. This also helps us confirm the planarity of molecules, whether a particular molecule is planar or not. So let's move on to the next example. Now you don't have to every time solve or pura mathematically solve karna hai. Now you can just look at a particular molecule and identify that. Let's say the next molecule that I have is PCl₅. What was the hybridization for PCl₅? sp3d. What was the geometry? Trigonal bipyramidal. Chalo, let's make iska shape. So this is phosphorus, Cl, Cl and Cl. Where were the remaining chlorine atoms? One of them will be above the plane and the next one was. Sorry. Now we first look at the equatorial bonds. Can I say equator pe PCl looks exactly like BF and BF. So will the dipoles cancel each other? And ye P and ye Cl ka dipole is in which direction? Towards. And ye P and ye Cl ka dipole is in which direction? Are both the dipoles, the one pointing up and one pointing down, equal in magnitude, opposite in direction? Give me PCl₅ ka net dipole is also 0. If I give you PCl₃F2, what was the difference in the structure? The more Bend's rule. What was Bend's rule? The more electronegative elements will occupy axial positions. So यहाँ पे आ गया एक fluorine and there's one over here. What about इसका net dipole? Will also be 0. But if I give you PCl2 F3, what about now? What difference do you observe? PCl2 F3. The F, which is the dipole pointing up and the dipole pointing down, they will cancel each other. But will the planar dipoles cancel each other? Because ye phosphorus and chlorine, and this is phosphorus and the net dipoles will not cancel each other. तो यहाँ पे the net dipole is not 0. Did you people get that? I repeat, why is it not 0? Phosphorus chlorine, ये phosphorus chlorine का जो net dipole है will not be cancelled by the net dipole on the left. ये जो right वाला dipole है will not be cancelled by the left dipole, and hence there will be some or the other magnitude. Did you people get that? Chalo. Okay, now let's do some questions together where we need to identify whether the net dipole will be 0 or non-zero. Okay, now let's start with the first molecule, CH4 sp3 hybridized tetrahedral. The net dipole in CH4 is 0. Similarly, CH4 की तरह you can also take CCl4 and even the net dipole in CCl4 is 0. SF6 people, net dipole is 0. IF7 में भी net dipole 0. XEF2, XEF4. So all of these have net dipole 0. But what about XEF6? XEF6 was distorted octahedral. Yeah, एक और geometry था उसकी capped. Excellent, capped octahedral. The net dipole here is not 0. Next, C2H4. What is C2H4? Ethene. तो अगर कुछ स्ट्रक्चर बना के हम देखें, so C and H में who is more electronegative? Carbon, especially because it is an sp2 hybridized carbon. तो डाइपोल का डायरेक्शन ऐसे होगा, ये डाइपोल का डायरेक्शन ऐसे होगा. Can you observe these two dipoles are cancelling each other? Similarly, ये डाइपोल ये डायरेक्शन में, the net dipole here, sorry, the dipole here is in this direction, so they are diagonally opposite to each other, equal in magnitude. Net dipole will be 0. Next, C2H2, which is ethyne or acetylene. We know that the hybridization is sp. H and sp hybridized carbon में ज़्यादा electronegative होता है, the sp hybridized carbon. Similarly, this H and C, who's more electronegative? The sp hybridized carbon. Again over here, the net dipole will be 0. Next, though we will study these examples again in organic, some of the examples I'll introduce them now itself. कुछ examples में एक दो points हमें नहीं समझ में आ सकते because we'll do that in organic chem, but for the time being take it as it is. यहाँ पे what we have is called as trans but2ene molecule, and this molecule here is called as cis but2ene. So if you look in trans, ये C और ये C में the sp2 hybridized carbon is more electronegative. This is sp3 hybridized. ये carbon here is sp2. So the dipole is in this direction. ये carbon और ये hydrogen का dipole is also in this direction towards the sp2 hybridized carbon. Can you see both the dipoles are in opposite direction, equal in magnitude, so they are going to cancel each other. ये hydrogen और ये chlorine का carbon, ये hydrogen and ये carbon. What will the net dipole be, people? But over here, this carbon and this chlorine dipole is in this direction. ये carbon and ये chlorine का dipole, people, are the two dipoles cancelling each other? Similarly, ये hydrogen और ये carbon का dipole is in this direction. Are these two also cancelling each other? No, they are not. So the net dipole is not 0. ठीक है? Now, you have CN group. CN group is called as cyanide. Cyanide में carbon is triply bonded to nitrogen. Carbon here is triply bonded to nitrogen. So the dipole here is in this direction. This dipole here is in this direction. It's a linear molecule, planar है. Net dipole is 0. But when you try to apply the same here to quinol, यहाँ पे the net dipole is not 0, and the reason is the molecule is not linear. The geometry is something like that. We will study about these molecules in organic chem, but what I want to tell you here is the same concept of dipole comes again in organic chem, where it helps us understand where exactly substituents are attached to the benzene ring. This is the second important application. Apart from knowing the geometry of the molecule, dipole moment will also help us understand in a ring on which positions what kind of substituent is attached. Depending upon the position where they are attached, some molecules may have net dipole 0, some of the molecules may not have net dipole 0. To study that, we'll take some more examples and some important exceptions as well. Now we're going to compare the dipole or the net dipole between first molecule that we have is ammonia and instead of hydrogen now we have 3 atoms of fluorine. Ammonia, what was the hybridization? Excellent, sp3, and hamari geometry 3. What was by geometry? It was trigonal pyramidal. So it was something like this. Nitrogen, ये रहा आपका lone pair, hydrogen, hydrogen and hydrogen. And similarly for NF₃, it would look something like this. Now between hydrogen and nitrogen, who's more electronegative? Nitrogen. So look at the direction of the dipole. All the 3 dipoles are in same direction. And यहाँ पे तो we have only electrons. So lone pair has a dipole of its own. If you see all the 4 dipoles are in the same direction, net dipole. I repeat, try to understand this. All the dipoles here are in the same direction, pointing upwards. But what about in NF₃? Fluorine and nitrogen, who's more electronegative? Fluorine. 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 And lone pair ka dipole will be in the direction of the lone pair. So what's happening here? There are 3 dipoles pointing in opposite direction and 1. However, lone pair ka dipole is actually stronger than the 3. But look at the net dipole. The size of the arrow, you can compare that and say that it's like the magnitude of the dipole. Who has greater dipole over here? NH₃. So the net dipole of NH₃ is greater than the net dipole of NF₃. So by just having more electronegative atoms in your molecule, you cannot say that a particular molecule will have more dipole or less. Now let's say the next dipole that I want to compare is between H2O and H2S. H2O, what was the geometry? Bent or V-shaped. What was the hybridization? sp3. Those sigma bonds the, if everyone remembers, and there were 2 lone pairs. The same here in H2S. Now, oxygen is more electronegative, dipole ये direction में. Similarly, ये dipole आप ऐसे direction में बना सकते हो. Net dipole. Same thing over here. There will be no difference. However, between oxygen and sulfur, who's more electronegative? And hence, in usual cases, greater the difference in electronegativity, I'm saying not always, but in usual cases, greater the difference in electronegativity, greater is also the net dipole. So, a similar example, maybe we can compare HF, HCl, HBr and HI. सबसे ज़्यादा net dipole किसका होगा? HF, then HCl, then HBr and then HI. Why? It is a simple difference in their electronegativity values. Fluorine is the most electronegative. Hydrogen, everywhere we have hydrogen, so the difference in electronegativity is maximum in HF and minimum in HI. However, there is an exception over here when you compare CH₃Cl and CH₃F. Now CH₃Cl, this is CH₃Cl, and this is CH₃F. H and C, who's more electronegative? This will be the direction of the dipole. Carbon and chlorine, who's more electronegative? And so the net dipole also is in this direction. Same thing is observed over here. But between carbon chlorine and carbon fluorine, who has higher electronegativity difference? CNF will have more electronegative difference because obviously fluorine is the most electronegative element in the periodic table. But the problem here is the net dipole of CH₃Cl is more than CH₃F. Now why is that as such? Remember people, dipole is a product of magnitude of charge into the distance. The distance or the bond length of CF is less than the bond length of CCl. So even though the magnitude of the charge developed is greater, I repeat, the magnitude of charge developed in CF is greater than the magnitude of charge developed in CCl, the distance over here between C and Cl is greater than the distance between C and F, making CH₃Cl ka dipole more than CH₃F. So if we want to write this for all the halogens, the trend would look something like this. CH₃Cl, then we have CH₃F, then CH₃Br, and then CH₃I. A similar trend, not an exception, CH₃Cl. If we perform chlorination, जो आपने 10th standard में किया है, in lower standards, which is more than CH2Cl2, CHCl3, and CH4, which is equal to CCl4, और इनका net dipole is 0. ये एक और ट्रेंड है जो हम याद रख सकते हैं. Chalo. Now let's do some questions. I want you to compare the following dipoles. Let's say I give this as molecule 1, 2, and 3. Which among the three will have the highest dipole, or I want to arrange them in decreasing order of their dipole strength or decreasing order of the net dipole. Let's start with the first one. Ye carbon and chlorine, who's more electronegative? So the dipole direction will be ऊपर ऐसा. इसका dipole direction will be down. Net dipole will become 0. What about here? इसका dipole is in which direction? ये dipole ये direction में, and यहाँ पे भी दोनों almost pointing up है. Now how do I decide between 2 and 3? Who has more dipole? One way to really understand is, see, both the arrows here are closer to each other and pointing in the same direction. Obviously 3 ka dipole will be more than 2. और a second way to understand this is, जो हम नेट डाइपोल का फॉर्मूला लगाते थे, रूट ऑफ a square plus b square plus 2ab. What is the angle between the two? यहाँ पे ये कितना एंगल हो गया? Excellent, which is 120 degrees. So this will become cos of 120. इसको हमने पहले भी सॉल्व किया है. This is what root of a square plus a square is 2a squared plus 2a squared into minus half. That becomes root of a. But what about here? Net dipole here will be square root of a square plus a square plus 2a squared cos 60. How much is cos 60? A squared plus a squared plus 2a squared into half. This will become a root. So if I want to arrange them in decreasing order of their magnitude, सबसे ज़्यादा dipole belongs to the third molecule. Then, so like this, they can give you any molecule. By knowing the formula, or even looking at the structure, you can identify which molecule has greater dipole. With me till here? चलो जल्दी जल्दी. Okay. Next we have people applications of dipole moment. ठीक है, लेक्चर में तो सारे applications बताए, but let's again go through what are the applications of dipole moments. The first application of dipole moment is to identify whether a molecule is polar or non-polar. If a molecule is polar, its net dipole will not be 0, and if it's a molecule is non-polar, then उसका net dipole will always be equal to 0. Second very important application is to decide the geometry of a molecule. Planar है, non-planar है, and it helps us identify where the substituent is attached in your ring. For example, ortho position पे attached है, or it is attached at the meta position, or it is attached at the para position. What ortho, meta, para or all these positions mean, ये थोड़ा और in depth we do in organic chem. And the next very important application is it helps us determine percentage ionic character. Now electronegativity difference पे we've already calculated ionic character in the chapter periodic table. We have written a special formula based on electronegativity. But we can also use dipole to calculate percentage ionic character. How do you calculate percentage ionic character? It's the ratio of the observed dipole to the theoretical dipole. How do you find the observed dipole? हमने dipole का already formula लिखा था. It is the magnitude of charge developed into the distance between the particles. Now over here, the distance between the charge is nothing but the bond length. And theoretical का मतलब क्या होता है? Let us say if I want to find the percentage ionic character in HCl molecule. So theoretical में what I am assuming that entire transfer of electron has taken to Cl. So let's see, ये जो cross वाला electron था that belonged to H, that now completely belongs to Cl. So we'll say that assuming कि there's 100% charge transfer, what dipole will be generated? That will be called as mu theoretical. Now let's take a numerical to understand this better. The question says for HCl molecule, the observed dipole is 1.2 dB. So 1.2 dB. We'll convert this into Coulomb meter. What is the conversion factor? 1.2 into 3.335 into 10 raised to minus 30. I'll keep it as it is. The bond length of HCl is given as 1.275 angstrom. I can use that to find mu theoretical. Mu theoretical का formula we had written charge transfer. H से Cl में there was transfer of one electron, so this is 1.6 into 10 raised to minus 19, which is charge on an electron, into bond length. How much is the bond length given? 1.275 angstrom. Angstrom को हमने convert किया into meters. And now we can easily calculate percentage ionic character, which will be 1.2 into 3.335 into 10 raised to minus 30 over 1.6 into 10 raised to minus 19 into 1.275 into 10 raised to minus 10 times 100. Solving this will give you the percentage ionic character. Okay? So this was ionic character of covalent bonds. The next topic, next class that we are going to do is hydrogen bonding, resonance, topic of bond order, and molecular orbital theory. That will complete one half of the chapter, which is the covalent bonds. Then we'll start with the second part of the chapter, which is ionic bonds. Okay? Thank you everyone. We stop for the day.